Alright, here we're going to take a look at using FEA 2D solver for a truss problem with this off-axis constraint. So we're going to learn how to handle those. Alright, so we're going to go straight from the empty Excel input template file. Pull it up on my opposite screen, it looks like. We'll go ahead and pull that over here. Open that up a little bit larger. And let's go ahead and save this under something meaningful. Let's go ahead and say Excel, input, and truss off axis constraint. Okay, so now we go ahead and take a look at our nodes. We'll keep this on the left side. We'll keep the problem on our right side that we can use for reference. Go ahead and make this a little bit smaller there. Touch smaller, there we go. Okay, so we're just gonna go tab by tab. So the first thing we'll go ahead and take a look at is our nodes. We have, let's see, 6 different nodes. So we'll go ahead and enter those in. Make this a little bit bigger just in case it's difficult to see. 2, 3, 4, 5, and 6. And we'll go ahead and start with assuming that the origin is at node 1. Don't have to, but we gotta choose some node. Why not node 1? Okay, so we'll go ahead and say that node 1 is 0, 0. Node 2, 8 meters over. We're gonna go ahead and use meters and newtons as our units. Meters for length, newtons for force. So we'll go ahead and keep that x distance as 8. Still 0 on the y's, assuming vertical is y. Node, oh, pardon me, I was thinking node 2 is node 4. Node 2 is up there, so that's only halfway across. We'll say that's 4, and that's 2 meters up. Going to node 3, that's 8 meters over and 4 meters up. Going to node 4, we have 8 meters across, 0 meters up. Going to node 5, we have 12 meters across, 2 meters up. Going to node 6, we have 16 meters across, 0 meters up. Alright, now let's focus at node angle. Alright, that's kind of an interesting stripe there. Let's zoom in. Still has that interesting stripe. I don't even know how I got there. Okay. Node angle. Node angle is the orientation of the node's local coordinate system, and usually it's the same as the global coordinate system, but it's meant for off-axis constraints. Why? Keep in mind that when we solve an FEA problem, finite element analysis problem, it is a matrix problem, and as we go from the global stiffness matrix to the reduced stiffness matrix, we have to remove degrees of freedom that are constrained. If we have something like this problem here, anytime, there we go, where we have a constraint at an angle, then what do we cross out? Do we cross out part of the degree of freedom in the x direction, part of the degree of freedom in the y direction? Well, the answer is you go ahead and assume a different orientation for that node. And that's exactly what we're going to do for node 6. So for node 6, we're going to go ahead and write in the number 45. And so what that means is now for node 6, the orientation of node 6's x-axis will be up along the slope, and the orientation of the y-axis for node 6 will be pointed up this way, and in other words, perpendicular to the slope. So that's what we're going to go ahead and do there. Go ahead and enter 45, and we'll just put in 0 for all the other entries. Okay, so that was the main difference with an off-axis constraint. The rest of this will look somewhat familiar to what we've seen before. So we have the various elements that we have. Looks like we got 9 different elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have, just connect the dots, right? So node 1 or element 1 connects nodes 1 and 2. Element 2 connects nodes 1 and 4. Element 3 connects nodes 2 and 4. Element 4 connects nodes 2 and 3. Element 5 connects nodes 3 and 4. Element 6 connects, where's element 6? 3 and 5. Element 7 connects 4 and 5. Element 8 connects 4 and 6. Element 9 connects 5 and 6. Alright, it doesn't matter really which one is node 1, which is node 2, as long as you have the correct nodes there. Alright, now we have our elastic modulus at 210 gigapascals. We are using newtons and meters, so that means we have to write in 210 e to the 9th to get in that gigapascal. Okay, we'll go ahead and write in our cross-sectional area at 0.001 meters squared. Looks like I put meters cubed there. I'll go ahead and change that. And this will be the same for all of our truss bars, so we'll just go ahead and pull that down. Now, since this is a truss model, we are going to assume that there is no area moment of inertia, so that there is no bending stiffness. And in other words, each of these truss bars can only take axial stiffness. And so for that reason, we'll go ahead and put 0 for our area moment of inertia. Okay. Similarly, we don't need to worry about the distance from the neutral axis to the top of the bar or to the bottom. That's only used for bending stresses. There is no bending stress because there's no bending stiffness for these elements. So we'll go ahead and put 0 for each of those. Drag those down. Okay. Release degrees of freedom. This is used primarily for frame elements when you want to release the rotational stiffness at a end to simulate a pin joint. But when we're looking at truss elements, it's only pin joints. So no release degrees of freedom, but we'll go put zeros for all of that. Coefficient of thermal expansion, that's only used for problems that have a change in temperature. We don't have a change in temperature in this problem. We'll put zeros for there. Okay. So now that's everything that we have for our line elements, all truss elements. They're only truss elements. Notice I didn't say truss or frame element. I just removed the bending stiffness, and that's what makes them a truss element. Okay, we're going to go ahead and take a look at our springs. No springs in the model. Moving on. Triangular elements, no triangular elements. Quadrilateral elements, no quadrilateral elements. Temperatures, we're not looking at a change in temperature. Keep going. Constraints. Okay, we need constraints in every problem. So we'll go ahead and go to where our nodes are constrained. We have only node 1 and node 6 that have constraints. Let's go ahead and make this a little bit bigger. Looking at node 1, that's pinned in both the x and y direction. So I'll take out degree of freedom 1 there. It's the same node 1. Now we'll take out degree of freedom 2. Now we'll go ahead and look at node 6. Now remember, we specified node 6 having a coordinate system that's rotated in the counterclockwise direction by 45 degrees. So if we go ahead and put node 6 here, we only want to constrain motion vertical to this, or perpendicular to this slope. And so where this would be, where if you can see the direction my cursor is going, if that's the new x direction for node 6, then this would be the new y direction for node 6. That's what we want to constrain. I'm going to go ahead and put node 2, or pardon me, degree of freedom 2 there for node 6. So this is referencing what we have all the way back here, right? It's referencing this, the fact that we have an oriented coordinate system for node 6. All right, let's keep going. So now we have our constraints. Move on to our loads. We have nodes 2, 3, and 5. So we'll go ahead and put node 2, 3, and 5. That looks like a better 5. And we can do a couple of different things here. We could say that there's no change in angle of force, and we have no load in the x direction, and we have minus 20,000 newtons in the y direction, no applied moment. Similarly, it does the exact same thing as if as what we have above. Is if let's assume that I have negative 90 rotation for my force angle, and then I applied 20,000 newtons. What does that mean? It means, let's assume that you have originally the x direction there, and then you rotate it 90 degrees clockwise. That's a negative 90. And now the x direction is pointed down, so we have 20 kilonewtons pointing down. Same thing as what we had before. Let's go ahead and take a look at one other way you could do this. Like, what if you wanted to do 90 degrees going up? Then we could go ahead and say that we have negative 20,000 newtons, right? Pointed up, we want the 20,000 newtons going down. That's why we have the negative sign there. Okay. any one of these formulations work. It's just a different way of entering in the information. All of these are doing the same thing, applying 20,000 newtons downward. Okay, and that's everything we have for our input file. So with that, we'll go ahead and save it. We'll close it, and we'll go ahead and reference that with FEA 2D Solver. So here we are still referencing this folder that has all of the FEA 2D Solver code inside of it. We're going to go ahead and reference this new Excel file, input file that we just created. Go ahead and copy that name there. I'll do a starting apostrophe, paste, end apostrophe. There we go. Units, remember we are using meters and newtons for our units. No temperature, but what the heck, we'll put Celsius in there. And let's see, create a text file results, why not? Graphical results, why not? Element numbers, great. No numbers, great. Okay, let's go ahead and run and see what happens. Alright, so we'll go ahead and take a look at the different outputs that we have. First, let's take a look at what our deformation looks like. This is exactly what we were expecting to see. Notice how this node actually moves off at a 45-degree angle. Let me go ahead and see if we can open this up and make it a little bit bigger here and really sort of zoom in to what we're seeing here. Look at that. So that node only moves upward along that 45-degree slope because that's the way that we constrained it. Great. So that's exactly like we expected it. Let's go ahead and take a look at a few other results that we have. Go ahead and take a look at our text file. We have our nodal results. You'll get your results for node 6. Note that the node 6 results are in that elemental coordinate system or the displacement coordinate system that we described. Now this is actually made to be similar or akin to what you might have if you run Nastran and you create a different coordinate system for a node. That's the way output would be there, so that's why this is output the same way. Shows us how much node 6 moves up along that slope, that 45-degree slope. Okay, and then everything else is pretty similar to what we've seen before. Let's go ahead and look at your line element results. We can double check to make sure that they are truss elements. Sure enough, they can't take shear, they can't take bending, just axial, because we only prescribed axial stiffness for those elements. Okay, one other thing, let's go ahead and take a look at maybe our global matrices. Okay, so with here, notice how our global matrix, we have K. Let's go ahead and double click that, and oh, not easy to make it bigger, and maybe we'll have K transformed. Oops. There we go, K transformed. Alright, make this a bit bigger. Okay, notice that these are like almost the same, but you see some values getting changed right in here, and sure enough, that's right about where node 6 is. And so essentially what that's indicating is that there was a transformation applied to the global stiffness matrix to account for that off-axis constraint so that this problem could be solved. All right, and with that, I think that covers most of everything that we wanted to cover for this truss element example problem with an off-axis constraint using FEA 2D Solver.